So we'll go to the next example, which is another ODE, and you know, they may seem repetitive, and but then sometimes we see some difference, right? The previous example, the first example showed in this class of examples, the first one is simply a warmer kind of a thing, basically v dot we showed, and then the second example has this integral kind of a thing, and then this one I don't even know what kind of Lyapunov function candidate. I have some parameters that I have to pick, right? So clearly this v of 0 is 0 and v of x is positive for non-zero. So that much is there, right? More importantly, we can even conclude that for all positive beta and alpha, we can even show that the basic condition of exponential stability is also going to be satisfied. So let's therefore compute v dot. Okay, so v dot is going to be 2 alpha x1 dot plus 2 beta x2 dot, right? Which when substituted, so I'm going to get 2 alpha x1 x2 minus 2 alpha x1 power 4 minus 2 beta x1 x2 minus 2 beta x2 power 4. By choosing alpha is equal to beta equals 1, this essentially going to give me minus 2 x1 power 4 minus 2 x2 power 4, which is of course strictly less than 0 for all x non-zero, and this is true all over Rn, R2 for that matter. So therefore we can actually, and then if you recall, this nice condition v of x going to infinity as norm of x going to infinity, and you can clearly see if alpha v of x now is basically x1 square plus x2 square, and that satisfies this condition. So we can conclude global asymptotic stability. Right? So we have this global asymptotic stability, but what about exponential stability, right? Unfortunately, we cannot conclude anything about exponential stability, and in fact, if we work a little bit hard, this is of the order 4, so this is probably in more like epsilon v square with a minus there, and one can actually show that in such cases you will definitely not have exponential stability, right? So it's a good idea for you to simulate this and see what happens. Okay, so this is a case where we have this global asymptotical stability, but perhaps not necessarily exponential stability, right? So that brings us to the next problem, which is another strange problem and becomes quite important at a later time. Is one of those where we have not just 0, 0 as an equilibrium point, but a bunch of other points, right? Now, clearly, what are the equilibrium points here? Basically, x1 is equal to 0 and everything else. Okay, if x1 is 0, both x1 dot and x2 dot is 0. Basically, the entire the x1 equals 0 line is the equilibrium point. So x1 equals 0 line is all equilibria. Okay, and this one v of 0 is not 0. Okay, we don't know what k is for the time being. That's a parameter that I want to leave it up and choose later. So v of 0 is not 0, so we are not going to show Lyapunov stability at this particular time. Okay, so perhaps it is, perhaps it's not. And what we are going to show now is basically use this particular function and use Lassalle's theorem, and then see what happens, right? And this is a lower bounded function, so that's one of the things that is required in Lasalle. If you have lower bounded, what happens is if v dot is less than or equal to 0, we can show that basically v has to reach some constant at some point, right? But if you recall, we need a bounded solution, but then this v is lower bounded, and then for some particular constant, if v dot is less than or equal to 0, then we know that there is going to be a domain of attraction, invariant set coming, the sublevel set of v is going to be invariant. Let's actually first check. So v dot is going to be equals to x1 dot plus 2x2 minus k times x2 dot, which is basically going to give me 2 alpha x1 square, okay, minus 2 x1 square x2, right? And substituting for x, this thing, we'll get plus minus 2x1 square x2. Sorry, I think there is something wrong here. Actually, this problem works only if this is one of these is positive, right? I'm going to assume that that part is positive. The first part is positive, so that way I'll get this plus, and this one will remain negative, and then of course we have minus 2k plus 2k x1 square, right? Therefore this will give me something like 2 times alpha plus k x1 square, right? So this and this will cancel. So what we can say now is basically, I don't know what alpha is, but I can choose k to be small enough such that alpha plus k, let k, right, be small enough such that alpha plus k is less than 0, right? So therefore we have v dot less than or equal to 0, but be careful, we are not discussing here Lyapunov stability, but more so some kind of convergence. So we have to look at this condition where v dot is equal to 0, and we use that in the theorem as r as x such that v dot is equal to 0. So that's same thing as x2 is equal to 0 on the dynamics, right? Sorry, is it x2? x1 is equal to 0, right? Let's recall the dynamics. So x1 dot is equal to, right, x1 dot is equal to alpha x1, I don't know the sign of this particular alpha, plus I made this change to x1 x2, is that correct? Yeah, sorry, yeah, no 2, right? And then x2 dot is minus x1 square, okay? So we have to look for invariant sets that satisfy this dynamics, right? Because on the invariant set, if something is true, it's going to remain, if x1 is 0, we know then x1 of t is going to be 0. So therefore in the first equation, x1 is going to be 0, x1 dot is going to be 0, so there's nothing that's going to come really much out of this particular dynamics. But in the second case, this implies x2 dot is going to be 0, right? So that means x2 is going to be constant on this invariant set, okay? So I don't know what that constant is going to be, but this basically essentially saying, right, something quite interesting. I showed that using this analysis, x1 is going to go to 0 and x2 is going to go to some constant, okay? And we know that the entire line x1 equals 0 has equilibrium. So it is going to an equilibrium point. Is it going asymptotically fast and things like that cannot be concluded out of this particular analysis. This is a purely analysis based on Lassalle's theorem that shows that if I'm going to start somewhere here, I conclude that I'm going to perhaps do all these crazy things and then basically reach some point on the line. I mean, it could have been something like this. It could have been like this. Okay, I mean, you cannot imagine a possibility of crossing this line because it has it's a line of equilibrium points, and one cannot do that in a finite amount of time. Once you reach the equilibrium point, you remain there, and then uniqueness will avoid anything like that, right? How do I know this whole thing is unique? This is entirely all the nice things about continuous differentiability and all those things there, so we can guarantee uniqueness. Okay, so that example showed an interesting way of showing convergence, but nothing is true. Nothing can be shown about the Lyapunov stability, right? Is it even true if it is Lyapunov stable? I don't know. Perhaps not. Right? For that to happen, if I can show, if I'm going to stay here, I'm going to come close to this, then we can show. But at this point, we have no idea. Right? So. But this is an example that is quite useful in something called adaptive control, and then we will look at that kind of logic at a later point. Okay, so we will again go through this exercise of not knowing what we are trying to do in terms of whether we are trying to show asymptotic stability or anything like that, right? So we have this two equations, x1 dot and x2 dot, defined in terms of some kind of ellipse, right? So here, on the other hand, we do have v of 0 is 0 and v of x is positive for non-zero. Okay, so it is a Lyapunov function candidate. Okay, it may even become a candidate for showing exponential stability, but we'll see, right? So the standard thing, as you've been seeing by now, we're going to compute x1 dot. So that's going to be 2 1 x1 dot plus 2 x2 dot, right? So I'm going to take the common thing, 1 minus ax1 square minus bx2 square times x1 times x1 will give me x square, x1 square minus x1 x2 plus x1 x2 plus x2 square, right? So this cancels, and then eventually we will end up with x1 square plus x2 square to 1 minus a x1 square minus b x2 square. Okay, and close to the origin, this is clearly positive, and therefore this system is most probably unstable. You know, we can actually use instability theorems to show that this is indeed satisfies all the condition of our instability theorems, especially the Lyapunov first instability theorem says that if we can find a v of x that has a positive point very close to the origin, and then we show v dot is positive over all and things like that, and then this precisely shows that, right? What more can we say? Okay, but then if you start outside this region, right, if you start outside where this is negative, v dot is going to be negative. Okay, so this is going to be positive. This is always going to be more than some particular number on the outside this region. So basically one can conclude that v dot is going to be strictly negative outside of this region. So if you start outside of this region, the fact that it is negative, so you can actually construct a big circle, right, in which this particular solution is going to remain there because v is decreasing. So let me draw a picture and then perhaps show. So we have this ellipse that's a x1 square plus bx2 square is equal to 1, right? And I'm somewhere here, right? So let's say I have this circle, okay, or even a bigger circle for that matter. If suppose the circle is something like this, one can actually think of a bigger circle like this, and then take that circle, and if you start anywhere in this circle, you know, because it's outside the ellipse, basically v dot is decreasing, so it cannot cross this boundary, this v is equal to some number, right? So it's going to seems like basically it's going to keep going and then perhaps cross the ellipse or not cross the ellipse, right? So we have a bounded solution, therefore it's an ideal candidate for using LaSalle's invariant theorem. When we actually take the invariant theorem, we need to look at v dot is equal to 0, and then when we see that x1 square plus x2 square is going to be you know, so I mean, you know, it's possible that that can get to 0, but then that means it's going to go to the origin. You know, that's a different possibility. The other possibility is this going to go to the ellipse, and using a little bit of logic, basically one could conclude wherever you start, you're going to actually end up going around this ellipse, right? So you know, LaSalle theorem essentially therefore can be used to show that if you are inside at the origin, you're going to go to unstable in the sense that it's going to go away from the origin. But if you're outside this particular circle, then basically we are going to reach this ellipse, right? And of course the question is basically, if we are inside, can we actually guarantee that reaching this particular ellipse, and then that's going to be left as a homework, right? So so we used LaSalle again to show some kind of dynamic behavior of a very different kind, right? So the last two examples I'm going to consider are something to do with instability. One using the first instability theorem of Lyapunov, and then the second one is using the second instability theorem, right? So if you recall, basically v has to have a positive number at some number very close to the origin, and then that's going to be clear on the line x1 equals 0. This is positive, so that's taken care of. So the only thing, other thing that we have to do is can we show that v dot is positive around the symbol, and just basically compute this 1 over v dot, and we'll essentially get minus x1 power 5 x1 dot plus x2 cube x1 dot x2 dot, which will give me when I substitute, I'll get x1 power 6 minus x1 power 5 x2 6 plus x2 power 6 plus x2 cube x1 power 6. And this is going to be x1 power 6 plus x2 power 6 plus higher order terms. Okay. Now, the nice thing about these higher order terms, when we actually, you know, let me actually do this a little bit rigorously. So I'm going to get this is equal to x power 6 times 1 plus x2 cube plus x2 power 6 times 1 minus x1 power 5. So the thing is, this x2 power cube and x1 power 5 is very, when close to 0, this you know, is going to be much smaller than 1. So we can find a small ball around which this is going to be positive, right? So that means v of x is going to be positive for all x in some small ball around the origin, showing x equals 0, 0, unstable. Okay, so that means you're not going to go anywhere close to the origin or remain bounded around the origin. So I mean, you know, what we have seen is basically show that V dot has these properties, right? So once again, we will take the last example of today's class is showing instability. And once again, V is positive on the line x2 0. So x2 is equal to 0. So therefore, one of the conditions for instability is shown very close to the origin. We have to have a bunch of points where x1 0, arbitrarily close point to the origin has to have a V of x positive. The only other thing is basically V dot should have either this positivity or something else. If you recall, we want V dot is equal to lambda V plus W, where W is non-negative and V is your this thing, the actual expression, right? For some lambda. So if I compute V dot is in this particular case, I'm going to get x1 dot twice plus 2x minus 2x2 x2 dot. So I'm going to get 2x1 square plus 4x1 x2 plus 2x1 square x2 square minus 2x1 x2 plus 2x2 square. Sorry, this is minus plus 2 x1 square x2 square. Okay. So sorry, this is going to be 4. Yeah. So this one cancels with this. So I will end up with basically something like 2 times x1 square minus x2 square plus 4x1 square x2 square, right? So this is your V, and this entire thing can be called W. So we get V dot essentially is going to be equal to lambda V plus W, where W is greater than or equal to 0, right? I mean, we have the theorem, but it's nice to see how this works out. If I actually, lambda is 2 in this particular case, so I can show that this is nothing but is equal to W, right? E power minus lambda t times V is going to be, derivative of that is going to be W. So basically V of x of t therefore is going to be V of 0 let me do this carefully, e raised to minus lambda t minus V0 is equal to integral 0 to t wt. Okay, but W is greater than or equal to 0, so that we'll get that. So eventually we can show that e power minus lambda t V minus V0 is Vt minus V0 is greater than or equal to 0. So that shows Vt is going to be greater than or equal to e power lambda t V0. And whatever the value of V0 unless it is 0, but then we do know at least there is one point for which this is positive. So this is take one of those points, starting point as in your initial condition, this is going to be positive and this is going to be exponentially increasing. So Vt is going to go off more than that. So Vt is going to go off to infinity if the solution continues forever, right, as t tends to infinity. So this is showing instability. Okay, I mean, this is the proof of that particular theorem that I presented the other day, Lyapunov's second instability theorem. So that is a sense how to solve various problems. The standard process is always use this V, find the V dot and analyze, right? Even in the case of instability theorem, that seems to be the standard case. So that ends the lecture on this problem solving. Next lecture we will actually focus on something much simpler than what we've been doing, but then we can go into many more details, and that's on linear systems. And eventually we use that knowledge of linear systems to understand, can we analyze nonlinear systems through linear systems? And that's the technique of linearization. And once we complete linearization, we'll have a series of techniques for nonlinear systems, to analyze, and eventually, of course, we can use those techniques to control nonlinear systems, right? So thank you very much.